Okay, well, good morning, everyone. So we start a new presentation here. We kind of are at two people who really changed the conversation for us, Eudoxus and Aristotle. We're going to move away from the speculative philosophers, as interesting as they are, and we'll put Plato in that category as well. Eudoxus, of course, is not a philosopher. He is a mathematician. He is actually a first-rate mathematician. And Aristotle is really not a speculative philosopher. That would be kind of unfair to characterize him that way. Aristotle is a different kind of philosopher. He's one who takes experience and looking at the world and taking observations as carefully as he can to try to, as he says, find first principles. Yes, he is a philosopher. He's not a mathematician. He's not really a modern scientist in our thing, but he does take observations very seriously, and he's looking for general philosophical principles. And if he can discover those using his observations, then he can make deductions. After all, he is the father of logic, among many other subjects. And so he can make conclusions from the principles that he derives from his observations. This is getting closer to the idea of science and we have of the pre-Socratics and even up through Plato, just kind of, I don't know, we don't want to call it wild speculations, but really ideas and theories which are really not necessarily grounded in observation in any kind of a detailed way. So these two people will, as we see, change the game, and we will then go forward with that different mindset, and it'll really take us into the world of science. So let's see how this plays out. But one last speculation. After saying all that, one last speculation. Here we have our two-sphere universe that we were left with Plato. We have the sphere of the earth, very, very clear that the earth is a sphere in the center of the universe, and we have the sphere of the celestial stars surrounding us, the fundamental two-sphere universe. And the idea is that the earth is fixed in the center, and therefore the celestial sphere is moving around us. And if you look at that right-hand arm is moving towards us, it's coming out of the page, right? And that's why the stars look like they rise in the east and set in the west. They come up out of the page and move across us, moving east to west. Well, Heraclides said, wouldn't it be much easier, instead of having the whole universe turned around us, wouldn't it be easier for us to simply just turn around in the center and leave the universe alone? And this is a wonderful speculation. And now it's not the first speculation that the earth is moving. Remember, the Pythagoreans had very much the earth moving around the central fire and all that. This is a little different here. Heraclides is a student of Plato and in fact of Eudoxus as well. And he's trying to just make a common sense observation that wouldn't it be simpler model, a simple idea of how the universe is constructed for just us to turn around once a day, as opposed to the entire universe turning around us once a day. A fair point. But the reaction was, yeah, Heraclides, it's a fair point, but it's a crazy one, right? Because the earth is not moving. Come on, we all know that if the earth were moving, we would feel it in some way. We would have some kind of other evidence, I mean, for example, how do the clouds keep up with the moving earth? The clouds aren't attached to the earth. If the earth is turning around, how do the birds even keep up flying in the, it doesn't make any sense that the earth is moving. Come on, And so this idea, as interesting as it is, and it is a fair point in terms of the economy of thought, was not accepted at all. So we have to kind of put it in the speculative camp. But we begin to think about Eudoxus and the first actual geometric model of the universe. And for that, we have to focus one more time here on the ecliptic, because the ecliptic and the sun moving around the ecliptic will be the fundamental idea, not only of his model, but actually going forward right through to Copernicus. So please, let's see if we can get this. Here's the path of the ecliptic through the stars. Notice the path is a winding one. That red line there, there's the celestial equator. That's nothing more than our equator thrown up to the sky. That's all it is. It simply divides that sphere of the fixed stars exactly in half the way our equator divides the spherical Earth. Okay. Notice that the ecliptic is sometimes above the celestial equator and sometimes below. Not surprisingly, in the summertime, it's above because the sun is high in the sky, and therefore it's high in the stars. And in the wintertime, here you can see in December, it reaches its low point in Sagittarius. It's below the celestial equator, and yes, in fact, the sun is low in the sky. So the path of the sun does not follow the celestial equator, but it does follow this very definite path over and over again, year after year. This is called the ecliptic, and it passes through all the famous and constellations of the zodiac, which were known by different names and different animals and different figures. All these patterns were, of course, well known to all the star watchers of civilization. So let's take a look at this again. Here is our two-sphere universe of Plato, and here is the ecliptic. Okay, the ecliptic is, of course, we have the Earth is straight up and down, and the Earth is the center of the universe, and the ecliptic is at an angle because sometimes in the summertime the sun is high in the sky, and in the wintertime the sun is low in the sky. And these are, in fact, the constellations. This is what the sun looks like in the sky. Okay, in the wintertime, it's in front of Sagittarius. And then as we get from the winter into the spring, it'll be in front of Pisces. And then for the summer solstice, it'll be in front of Gemini. And finally, in the fall, it'll be in front of Virgo, and on and on and on. It passes through these stars as we've seen as it goes around. Now, here's the fundamental idea that Eudoxus gives us that will stay with us through Copernicus. You see, what Eudoxus wants to build a mathematical model of the universe, as Plato said for the astronomers to do. And it's a mathematical model. He wants to build a geometric model. We have the celestial sphere moving around us every 23 hours and 56 minutes. We have the sun moving around us every 24 hours. What Eudoxus could have done, okay, and maybe this is what would occur to you the very first time, is that yes, the celestial sphere is going around us, around and around and around every 23 hours and 56 minutes, and the sun is going around us every 24 hours. Simple, two simple motions, and that's why the sun is falling behind. That's why the sun seems to be moving backwards, moving east in the sky, because it's simply not keeping up. Okay, it's going around every 24 hours as opposed to every 23 hours and 56 minutes, and it's simply falling behind. And it's falling behind along this path we call the ecliptic. This is not how Eudoxus saw the problem. This is not how he analyzed the problem mathematically. And his analysis is slightly different, not at all complicated in that sense, but it gives an independent motion to the sun on the ecliptic as it's being whirled around every day, every 23 hours and 56 minutes. What Eudoxus sees is as the sun here, okay, is being whirled around and around and around because it's being carried around by the sphere of the fixed stars, it has an independent motion that it creeps along the ecliptic 1 degree backwards every day. Why do I say backwards? Because the celestial sphere is turning this way, right? This edge of the celestial sphere is coming at us, but the sun is moving the other way. It's falling backwards 1 degree. And this is what Eudoxus, and this is what all astronomers after Eudoxus who use this model mean by saying that the sun goes around the Earth. We are not talking about the daily motion of the celestial sphere going around the Earth. Yeah, we got that. When we talk about the sun going around the earth once a year, we're talking about this very slow motion of 1 degree every day, moving backwards through the stars, going through the constellations of the zodiac, 1 degree every day, while it's being spun around and around and around, almost without its consent by the celestial sphere. This idea is absolutely fundamental, guys, for you guys to get this. Otherwise, it really won't make any sense when we talk about the moon going around the earth and the planets going around the earth. If you're still thinking about the swirling of the celestial sphere going around once a day, you will have missed the whole point of the planets moving very slowly through the sky with their retrograde motions, very slowly on the ecliptic, or sometimes above and below. It's that second motion that Eudoxus gives us to build his geometric model. Let me show you an animation, and then I'll take a question on this if it is not clear. I really would not like to go forward unless we're all comfortable with this idea of 2 separate motions that the sun has. Let's see if this animation can help. Okay. So let's get our bearing. Here is the good green Earth in the center. Here is our celestial sphere. This is our 2-sphere universe. Okay? And here is the ecliptic. Here is the path that the sun makes through the sky once a year. And this is the position of the sun right here in black. This is our black sun. And I've marked in red this arrow, this line, to show us this is where the sun is right now, today. It's on that point in the ecliptic. It's behind these stars right here, this constellation here in the zodiac on the celestial sphere. So this is where we see the sun, and behind it is that piece of the celestial sphere, some constellation of the zodiac. Let us let the earth now, let us let the universe turn once a day. Okay. We'll let it turn once a day, moving east, right? Imagine that the map of the United States here. So this is east and this is west, and the stars are moving this way. So the stars are moving from east to west, rising in the east and setting in the west. And the sun is being carried along on the ecliptic. The ecliptic is being carried along because the ecliptic is this path through the stars. It's carried along. It's carried along for the whole day. And when we get to the next day, what we find is that the sun has fallen behind. It's fallen behind empirically because it took 24 hours to get around, and the ecliptic only took 23 hours and 56 minutes. But how Eudoxus sees it is it's fallen behind because it's literally moved on the ecliptic. It has moved just the way it seems to have moved. It seems to have moved backwards. And notice again, if we can see the map of the United States in front of us, we can see here California on one side and the East Coast on the other side. And yes, the sun has moved backwards. It has moved east 1 degree each day. And of course, I'm exaggerating all these motions so that we can see it more easily. This is clearly much more than 1 degree. So think of this as one turning of each month. As each month goes by, we'll let another month go by, the earth being turned around and around and around every day. And what we find is now back to. He started here. He was here last month, and now he's here this month. He's moving backwards little by little by little, having an independent motion on the ecliptic as he goes around the earth. And by going around the earth, he's actually going around through the stars, which of course is what we see. And this is what Eudoxus, and this is what Ptolemy, and this is what Copernicus will mean when all Copernicus is going to do is change the model and put the sun in the middle, and the earth is going to be going around separately, little by little, as it's turned around and around and around. This fundamental idea of 2 separate motions, not one motion just slower than the other, is the fundamental idea of this model, and it will stay with us for over 2,000 years. Questions? Someone want to unmute themselves, ask a question, make a comment, make a clarifying comment, do a better job than I did in explaining this. Any question about this? Okay. So let us take that as the fundamental idea and see what Eudoxus does to build his model. Let me just go ahead and open up next one in case we get that far. We'll open up this one and close that one because we're done with this. There are no questions. We're good on this. Okay, I will close this up and leave this guy for later. Okay, so notice we only really need two spheres here to explain the motion of the sun. And it's really kind of simple if you think about it, okay? There's the outer sphere with the fixed stars, and they're turning around and around every 23 hours and 56 minutes, and the sun is creeping along its path 1 degree every day backwards, and that's why it takes 24 hours to get around. There's our day, straightforward explanation, and there's why it moves through the stars. We see it moving through the stars. We see it moving through the 12 constellations of the zodiac because it's literally moving around 1 degree every day, a little bit less than 1 degree every day. So instead of taking 360 degrees, 360 days to get around 360 degrees, it takes 365 days to get around because it's not 1 degree, it's 0.92 degrees going around. And that is this fundamental idea of the two separate motions of the sun. Okay, let us now go to Eudoxus's model. This is the first mathematical universe that we have in Western history. Okay, Eudoxus, as you can see, his dates a contemporary of Plato. He was actually a student of Pythagoreans, as Plato was. He even apparently attended some lectures of Plato in Athens at one point. But an independent genius himself, he went ahead and moved up into the Black Sea area and started his own school actually with an observatory as an astronomer. And he is, like I say, a first-rate mathematician, as we will see. He is considered the greatest mathematician of antiquity after Archimedes, and that's always true. Archimedes is not only considered the greatest mathematicians of antiquity, he is considered one of the greatest mathematicians of all time. So just to say for a moment what the kind of mathematics that Eudoxus is responsible for, just to give you an idea of the scope. Well, let me finish this thought here of just his model. We have this picture here, which I'll explain in much more detail in a moment. But he has this notion of each of the planets, each of the 7 planets, got to get into the Greek mindset. The 7 planets are the sun, the moon, and the 5 regular planets that we think of as planets. He's trying to show the position in the sky geometrically of these 7 planets. And what he needs is he needs 3 independent spheres for the sun, 3 independent spheres for the moon, and 4 each for the planets. And one final, the big sphere, the outer sphere, which is moving the fixed stars every 23 hours and 56 minutes. So altogether, he's got 27 mathematical spheres. These are not real spheres. He doesn't worry about how the gears work to make one turn around the other. He just posits these mathematical motions. He's a mathematician who's not trying to develop a physical model, okay? Actually, Plato dissuaded the astronomers for trying to think about a physical model because he says there's no way we'll ever know how the perfect forms up in the sky actually really perform their magic. There's no way we'll ever know that. What we want to do is create a mathematical model to show where they are in the sky. That's really the best that we can do. And this is what Eudoxus set out to do. So this is very much a mathematical model, not a physical model. Aristotle will come along and want to build the physical model, because of his way he thinks about the world. But just for a moment to mention Eudoxus's mathematics, he's very famous for two other things besides the model that we're going to go through, is in the world of mathematics. And both these pieces of math are found actually in Euclid, who lived slightly after Eudoxus. The first one is the so-called method of exhaustion, which is the pre-runner of the integral calculus. And the idea is to find the area of a circle. To find the area of the circle, if you can go ahead and find the area of these polygons, which, you know, geometry of the day could find the area of these various polygons, as you make the polygons have more and more sides, you can see we kind of exhaust the area of the circle. At the area of the polygons, as you get more and more sides, are getting closer and closer to the area of the circle. This fundamental idea, which was not Eudoxus's idea, but this fundamental idea he takes and makes into a mathematical method. He makes this thing rigorous. And by doing this, he essentially invents the idea of limits and the idea of the integral calculus for those of you who've taken calculus. He pretty much applies his method really just to the simple figure of the circle, and that's what we see in Euclid. Okay? Archimedes will come along 50, 75 years later and turn this into a incredibly powerful mechanism, and works way beyond circles, finding the areas of all kinds of figures, both plane figures and three-dimensional figures. He starts finding the lengths of curved lines using this very same method. And that is why Archimedes is very much generally considered by mathematicians the inventor of the integral calculus. He took the fundamental idea of Eudoxus and broadened it and generalized it, and stayed that way until the scientific revolution. Mathematicians went ahead and began to develop the calculus as we know it. The other great contribution that Eudoxus made is he solved the problem of the irrational numbers. The irrational numbers really threw the Greeks because they didn't know what to do with them. They weren't numbers that they didn't have a handle. They were geometric entities that they could handle. Okay, you know, the diagonal of the square was a perfectly fine line. Its length was a real problem. And because of that, given the importance of, for example, similar triangles in Euclidean geometry, there was no way to actually show that these two squares, or let's say the two right triangles below it, the two right triangles created by the two lower pieces formed by the diagonal, to show that those two right triangles were similar. They actually had no, because of their demand to be very, very rigorous, their logic had to be very, very rigorous. The similar triangles required proportions, and proportions required numbers, and they didn't know what to do about the numbers involved in those lengths. And it's Eudoxus that went ahead and solved that problem. He solved it by giving a more general definition of what a proportion was. He actually anticipated the definition, the modern definition of irrational numbers that was not discovered until the late 19th century. He gives a geometric version of how to consider these proportions, even though they're irrational lengths, so that they could fit in and be harmonious with the normal rational lengths of fractions, so that you could go ahead and deal with these two triangles and call them similar and prove similar properties of them, and go through the Euclidean geometry that we all know and love. It's Eudoxus who got us past the hurdle of being able to deal with these kinds of lengths, irrational lengths inside of our figures. So these are the two great mathematical contributions of Eudoxus. Well, let us go back to his model. I say he needs 3 spheres for the sun. He actually only needs 2, the 2 that I showed you. I'll show you the 3rd sphere. Remember, this is a mathematical model. So this first sphere causes the outside sphere. That's the celestial sphere. And we know that turns that way, right? That right arm is coming at us, coming out of the page. That little dot here, here's the Earth in the center. Okay, and think of the map of the United States here. So the sun is the stars are all coming at us. They're all rising in the east, from the east coast. So there's a celestial sphere. He needs that sphere for the sun. This is in addition to the celestial sphere. He needs these three mathematical spheres to make the motion of the sun. He's got the big celestial sphere, the real one that's actually turning the stars, and now he needs three more. He's not worrying about the fact that he could have used double duty, the real celestial sphere to move this. He's not concerned about that. He's not concerned about building a physical model. He's only concerned about building a mathematical model to get the positions of the 7 planets and, of course, the stars correctly. The stars are almost free. You sprinkle the stars according to the patterns of the sky watchers. You can have them turned every 23 hours, 56 minutes, and voila. That is the motion of the stars done. Okay, they've been moving that way forever, and they will move that way forever. You give me any date in the past or the future, I'll whirl this thing backwards and forwards, and I'll tell you just what the night sky looked like at any time. Solarium done, okay, by just that one sphere of the fixed stars. Not a big deal. The sun also is not all that difficult once you get the idea of these two separate motions. So we have the motion of the celestial sphere turning the sun around and around and around every 23, 56 minutes. And you have the inner sphere here that's turning this way because the sun is moving to the east, very, very slowly creeping around as it's being whirled around and around. It's creeping around once a year through the fixed stars. And these are the two spheres that he needs. He actually talks about a third sphere in which he says you have to have this third sphere moving also slightly around to adjust what's called the longitude of the sun on the ecliptic. Eudoxus has this notion that the sun is not always exactly on the ecliptic, which of course is not true. That's the definition of the ecliptic. But he has this notion that he thinks that the sun needs to be able to move the sun a little bit above and a little bit below the ecliptic as it goes around. This is not true. This is a misconception of the astronomers of his time, and he actually doesn't need this sphere at all. The two spheres, as we described in the previous slide, will do. But for historical accuracy, he has three spheres for the sun and for the moon. This basic building, notice it is not just a model of tables like the Babylonians. This is not just a numeric model. The numbers come from the geometry. That is absolutely vital. The fundamental model is a geometric model. And once you put the sizes and the speeds of these figures inside the model, the numbers will come out. The numbers are computable from the more fundamental numbers of the rotational speeds and the diameters of these spheres and the interlocking of these spheres. That's where the numbers come from. The geometry comes first, and this is fundamental, and this will stay with us until today. This does not change. Newton does not change this. Okay? Einstein does not change this for general relativity. Okay? It is the geometry first, and then the computed numbers come from it. Okay, so just one last look here at this all-important notion of the dual motion of the sun. Okay? We have the sphere of the fixed stars with this rotation going around and around this way. You can see the arrow turning this way so that the stars will rise in the east and set in the west. And here's the sun moving along the ecliptic, sometimes high in the sky in the summertime. Yeah, because when the sun is up here up in the sky, as it's being turned around each day, it's very high in the sky. Okay, this is the summertime. When it's down below our celestial equator, well, we still see it from where we are, but it's low in the sky, and this produces our seasons. Okay? This model, by the way, that you're looking at, this is still taught today in astronomy class. When you begin astronomy, if you want to begin with positional astronomy, what the sky looks like as opposed to black holes and the interior of stars, if you start with the basics from a star kind of course, where you begin with understanding the motion of the sky, this is the model that you're taught today. Okay, it is the simplest way to think about the sky. It's when you sit out on your lawn chair at night, this is what you see. This will explain in the simplest possible way what you see night after night. this model is still very, very valuable and still used. So there is the axis of the ecliptic sphere turning around the opposite way to make the sun slowly creep along the ecliptic, moving east. Okay. And again, these are not physical gears. Eudoxus didn't trouble himself with trying to create the physical mechanisms that would make these things happen. He was a mathematician, and getting the math relationship right is all that he was concerned about. This is all that Plato asked for. Okay. So Eudoxus did have an idea of how big the sun was and how far away it was compared to the moon, for example. And Archimedes reports, in talking about Eudoxus, that Eudoxus said that the sun had its diameter of 9 times greater than the moon. You don't know why. Archimedes doesn't tell us why Eudoxus felt this, but in his writings he does mention this. So again, we have these quantitative speculations without any proof, without any evidence. They're still throwing out other mathematical properties, physical properties of the heavens, but again, we're not getting any evidence for some of these yet. Okay, let's take a look at the moon, and then I'll stop for questions because I don't want to move to the planets unless we're comfortable with this idea. Here, the moon, we do need 3 spheres. We do actually need 3 spheres, and we'll start with the celestial sphere, okay, with its axis, and it's turning around. All the celestial spheres turn around the same way every 23 hours and 56 minutes, allowing the moon to rise in the east and set in the west, because it's being carried by the celestial sphere that's doing that. So the moon is being whirled around and around and around every day, just like the sun is, just like the ecliptic is, just like the planets are, just like the fixed stars. They're all on the same daily merry-go-round. And here is the axis of the ecliptic, turning the opposite way so that the moon will creep along, moving east through the sky. But the moon is so slow that it moves along much faster backwards so that it can get around in a month. Okay, it can move 12 degrees through the sky every day. So it just takes a month for the moon to go all the way around the stars, all the way around the zodiac, which we call a month. And finally, the last sphere is the sphere, this slight adjusting sphere, which will kind of make the moon tilt a little bit sometimes off of the plane of the sun going around the earth. Let me show you what I mean. This plane here is, if you extend this plane out, will contain the sun. The sun is moving around the earth in this plane. This is the plane of the ecliptic. Sometimes it's high, sometimes it's low. But the sun will stay in this plane. The moon does not move always in this plane. In fact, sometimes it's a little bit lower, below the plane, and sometimes it's a little bit above the plane as it goes around and around through its cycle. The whole cycle takes 19 years to complete the whole cycle of the dance between the sun and the moon. See, if the moon was in the same plane as the sun, then every new moon would be a solar eclipse. And every full moon would be a lunar eclipse. But we don't have that, because when the new moon is in front of the sun, it's not directly in front of us. It's generally higher or lower. Okay, and so we do get a dark moon, but it's not right in front of the sun. Okay, that's because the moon is not in the same plane as the sun is as it goes around. It dips above and below. Another picture here. The moon actually will be sometimes 5 degrees above the plane of the sun and sometimes 5 degrees below. So as the moon is turning around, it actually, if we would look at it from this vantage point, the moon seems to slide back and forth as it's making this circle that we can't see. And sometimes it does be in the plane of the earth. And if it's at the plane of the earth, just at the new moon, a rare event, then we'll get a solar eclipse. Okay. So this, we do need, Eudoxus did need this third sphere to slightly adjust the longitude of the moon as it went around the sun. And he got that right. Okay. Again, I'll stop for questions. Are there any question? Can anybody ask a good question? A good question could be very valuable here, because this is not easy to, if you're seeing this for the first time, there's all these arrows and spheres and axes, and this is not easy to absorb necessarily the first time. And I'm not sure I'm doing the best job explaining it. Can anybody make a comment or a question?
So I'm wondering, when did the notion of tilting, the Earth tilting, come in?
That had to be with Copernicus. When Copernicus finally sets the Earth in motion, he has to tilt the Earth to accommodate the ecliptic being on its side. Any other question? Comments? All right, well, let's move into the motion of the planets. Right? This is the difficult thing. Again, notice that with the moon, it's not all that tough. This model really gets the position of the moon. You can tinker with the axis, change the degree of the axis. You can change the speeds, independent speed slightly, but you can get the position of the moon in the sky here at any time in the past and any time in the future by getting these numbers right. It just depends on how accurate your observations are that will determine what these different angles should be and what these speeds should be. Okay, if you've got good data, there's no reason why once you have the model built, once you can see the model, once Eudoxus gives us the framework to work in, with good data, any competent mathematician can put this together and get the motion of the moon pretty well. Okay. It's the motion of the planets which are very, very difficult, primarily because of the retrograde motion. So let me show you how he tackles just the retrograde motion. He needs 4 spheres. We already know about the first 2. That's the celestial sphere and the ecliptic sphere. These are the 2 spheres. We're just going to focus on the 2 inner spheres that he needs to create the retrograde motion. And he creates this very beautiful, elegant mathematical curve here called the Hippolyte, this kind of figure 8 kind of thing. And this Hippolyte is carried around and around using the other 2 spheres. And here's a nice animation of just those 2 inner spheres. He's got a green sphere and a red sphere. And the green sphere is moving around its axis, and the red sphere is moving around its axis. And the planet is simply moving back and forth. It's oscillating back and forth on that moving red sphere. And he's going to take this figure 8 and whirl it around the ecliptic very slowly, once a year, and that whole thing will be whirled around every day, every 24 hours, every 23 hours and 56 minutes. And the combination of all of these 4 motions simultaneously gives you pretty well the position of a planet in the sky. It's a really ingenious piece of geometry. Clearly, we do not have the time or even the background. This is not, we don't want to go into this level of the math. We're not, that's not the math that I can assume that we have here. So we'll just try to get the fundamental idea. What's interesting for us is, remember that in building this mathematical universe, he's building this thing 1 planet at a time. All these sets of spheres are independent of each other. The 4 spheres for Jupiter are completely independent of the 4 spheres of Mars, for example. Now, yes, the celestial sphere is the same, okay? But the 2 inner spheres are completely different to create the retrograde motion of Jupiter compared to the retrograde motion of Mars. What's interesting, when you look at his model for Venus and Mercury, yes, the celestial sphere will be the same as everybody else. The ecliptic sphere will be the same as everybody else, but their speeds, the ecliptic speed is the same for both Venus and Mercury. The ecliptic sphere for Mars is very, very different. It's much slower. Mars goes around the ecliptic in about 2 years. Mercury goes around it in about 88 days. Okay? So the ecliptic sphere may be the same, but the speeds are quite different. What's interesting about these two inner spheres of the planets is that the green sphere is the same for both Mercury and Venus. This is the first hint we have, and it shows up in his mathematical model, that there's something special and allied with Mercury and Venus that even the math has to conform to it. There's something common about Mercury and Venus that are not shared by not only the rest of the planets, but even the planets themselves don't have that kind of sharing. They're independent, but Mercury and Venus have some kind of dependency somewhere. And of course, this will become much more elaborate as we get to the model of Ptolemy. And finally, the full explanation of it will come clearly with the model of Copernicus. What's the fundamental weakness of Eudoxus' model as we leave it? These are all concentric spheres, guys. The planets always have the same distance from the Earth. They're riding on concentric spheres inside an onion, and they don't change their distances. This is not such a big problem for the sun, but it's a problem for the moon. You could see that the moon does have different sizes to it, and clearly it's a big problem for the planets, okay? Mars changes its brightness dramatically. Venus and Saturn also change their brightness dramatically. Everyone agreed that the changing brightness is because of the changing distance. When the planets were close to us, they were brighter. When they went further away, they got dimmer. This model does not accommodate the changing brightness at all because it doesn't accommodate the changing distance. The explanation? Eudoxus is a mathematician. He set out to describe mathematically the positions of the planets in the sky, not the physical model of actually where they are in the sky, not the three-dimensional picture of their different distances. This is not what he set out to build. And as any good mathematicians, he is going to take one aspect of the problem and try to solve it. And once he has that solution, he can then build on that solution to generalize it to more aspects of his universe, which he never got to, at least that we don't know of. So he did solve very, very beautifully, very elegantly the positional problem with his model. I'll stop one more time before we leave Eudoxus. Can I answer any question about the concept which Eudoxus gives us, not the details? Let's not worry about the details of this thing. You may have some detailed questions. Please shoot me an email, and I'd love to discuss this with you. Is there anyone who is having a problem just conceptually of what Eudoxus has done here with Plato's two-sphere model and bringing in basically the third sphere of the ecliptic and having the sun and the moon and the stars slowly move independently through the stars on the ecliptic as a third separate motion, as a second separate motion. Anybody have a question or a comment? Okay, well, we will move on then to his contemporary, a true student of Plato, Aristotle. Aristotle comes from the north. He's a hick from Macedonia, comes to Athens. His father is a nobleman, doctor to the king, a king who was the father of Alexander the Great. And he comes and studies with Plato for many, many years, becomes his star student. Plato is the first professor of history. He writes textbooks. He writes on all kinds of subjects, textbooks on all kinds of subjects. His theories are quite amazing. His theories dominate Western thought. all of Western thought. When I talk about Western thought, I talk about also the Islamic culture and during our dark ages, from the Pillars of Hercules to the Indus River, that part of the globe, the Western world, his ideas, which we'll go through some of them now, will dominate for 2,000 years. That is really quite unprecedented. Newton's theory of gravity and mechanics only lasted for 350 years before it was overturned by Einstein, general relativity, and by the quantum mechanics. His world lasted 350 years. Aristotle's lasted 2,000 years. Okay. So what can we say about, yeah, I want to read that quote underneath. Knowledge or understanding comes only when we have discovered first principles. He's still a philosopher. He's looking for first principles. How does he find first principles? He finds them, though, through what he can do with observations, as detailed observations as he can. He makes an honest effort at looking at the world, seeing how it really works, not how it's supposed to work, like the Pythagoreans, and trying to come up with first principles. And then once he has those principles, he can then justify or explain why other things are true, or he can make deductions from those principles. And so advance knowledge based upon the logic that he has coming from these first principles. This is going to be his methodology, as we will see. So we'll take a look at his cosmology. It's all written down in one of his famous books called On the Heavens, De Caelo, the Latin translation. And he says this. He says, the world below the orbit of the moon is composed of the four basic elements, earth, air, fire, and each element, each of these elements has a natural motion and a natural resting place. Well, this is what he sees. He sees heavy objects naturally want to fall down. He sees earth and water, which are heavy. They naturally want to fall down. He sees air and fire naturally move up. Look at a fire. The flame is always moving up. Okay. You look at the smoke coming up from a fire. It's naturally moving up. These are the natural motions that they have. They don't need a cause. They just do that's their nature to do those things. Why do they move that way? Because they want to go to their natural place. Heavy things want to move down because their natural place is down there somewhere. So the earth and water, they have a natural motion. They move straight down to the center of the universe. This is his principle. This is where they move. Air and fire, they move straight up towards the orb of the moon, because at the orb of the moon is when the new waters appear. Plato's new world starts. That Aristotle agreed with. This is the world of the ether. This is the world of that third substance. This is the world of the divine. Okay? Plato had it just as the world of literally the divine, literally of the forms of the ideals. Yeah, Aristotle's not going to go for that. This is going to be just a third substance, a very different substance, something fundamentally different than earth, air, fire, and water, but indeed a substance that he called the ether. Any motion which is not natural has to be caused by some kind of a continuous contacting force. This will become very important as we go forward. We're not going to deal with this too much now. We'll deal with this a bit later, his detailed theory of motion. But it's important to recognize this now. For example, if we were all together, I would be pushing a book along the floor, along the desk right now, and showing you what Aristotle is saying is, as long as I'm pushing the book, it'll move. As soon as I stop pushing, it stops moving. Why? Because the book moving along the desk is not its natural motion. Oh, if I were to let it drop off the edge of the desk, it would move into its natural motion and hit the floor, because that's where it naturally wants to go. It naturally wants to go to the center of the universe. But moving along the desk surface, no, that's not natural. That needs a force. It needs an outside cause. All the heavenly bodies are perfect and divine, if you like, and therefore they move about the earth in the most perfect motions, unchanging perpetual circles. Notice the deduction. Because they're perfect, they must move in perfect motions. What else would perfect things do? How else could perfect things move? Not perfectly, if they're perfect. What's the perfect motion? Well, everybody knows what the perfect motion is. That's eternal circular motion. The heavenly bodies are not made of the earth, air, fire, and water, but a fifth very definite substance called the ether. It's kind of a weird substance. You can't see it. It has no weight. It's invisible. It's perfect. It has a different natural motion, but it is a substance in Aristotle's book. And so since the heavenly bodies have only their natural circular motion, because that's the natural motion of the ether, they're never subject to any kind of a force. And therefore, since they're perfect and they move in their own natural motion, catch this now, since they're moving in their natural motion because they're perfect and the natural motion is perfect circles, therefore they must move at natural speeds. I'm sorry, at constant speeds, because there's no force required to move them. Only a force would make them move faster and faster or slow them down. Since there's no force, of course, they must move at constant speeds. You see the deductions coming from things that we know, things that we agree to, that the planets move in constant speeds or combinations of constant speeds. Well, this is why they do that. We're getting this from our first principles. Okay, so let's look at some deductions that Aristotle can make. The earth is at the center of the universe. Well, that's an easy one. Proof, well, the earth is composed mainly of the elements of earth and water. Duh, yeah, that's true. Their natural place is the center of the universe. Why? Well, it's because when you see things fall, that's where they naturally go. So the natural motion is towards the center of the universe. So, well, where does the earth and water going to go? They're going to go to this. Well, where is the earth going to be? There's no force that could possibly change where the earth's going to go. The earth is the 800-pound gorilla. If the earth wants to go someplace, it's going to go there. No force can possibly be great enough to move it artificially out of its natural motion. And therefore, the earth belongs in the natural place of earth and water, which we've already agreed to is the center of the universe. QED. The universe is finite. This is a nice one. This is actually proof by contradiction. This is a method of proof, which, as the founder of logic, is the first one who actually wrote a book, a textbook on logic, laid out all the different kinds of logical arguments. And this is a very important one. This is one that Euclid uses very, very often in his geometry. This is called proof by contradiction. The universe is finite. Well, suppose it's not. That's how you begin a proof by contradiction. Suppose the universe is not finite. Then what's going to happen? Well, if the universe is infinite, then infinite things don't have a center. Any place is as good as any other place because the universe is always infinite no matter where you are. Okay? So you're always surrounded by more infinity. So the universe has no center. But we just agreed that the earth is at the center of the universe because of all that natural motion business. So the universe does have a center. Well, therefore, the universe must be finite, can't be infinite. This is a classic proof by contradiction. Of course, Euclid will take this a very sophisticated level, proving beautiful, intricate theorems of geometry. But this is an example of this argument form that Aristotle writes about and pieces, pulls together, pulls apart, and analyzes in his book on logic. The earth is at rest. That's also an easy one. We've shown that the earth is at its natural place. It's at its natural place. Who is going to move the earth? Okay. And therefore, there's no tendency for it to move. It's already where it's supposed to be. And there's no force that's going to move it. What force could possibly be big enough to move the earth? There's no violent motion that could do that. So the earth is going to stay where it wants to be. The earth is clearly at rest. And the earth is a sphere. Okay? Here's where Aristotle is very interesting and very valuable to us. Aristotle will go through the three arguments of the Pythagoreans, giving the evidence that the earth is a sphere. He's very happy to do that. He's very happy to summarize the thinkings of the previous thinkers that came before him. Actually, he's one of the great sources of our knowledge of the ancient world. By reading Aristotle's textbooks, the first thing he'll tell you is what so-and-so thought and why they thought it, and then he'll disagree with them, basically. So, well, that's all wrong. And so this is where we learn in Decatur where those three arguments that I gave you of the Pythagoreans for the round Earth, the ship moving back and forth, and coming out of the water, and the spherical edge of the lunar eclipse, and the changing horizon as you move north and south. These arguments are given to us by Aristotle, and he says these are from the Pythagoreans. Pythagoreans had these arguments, and they're good arguments. But why is the Earth a sphere? That's a totally different question to Aristotle. That's the fundamental question. That's the more important question, because there must be some principle involved to reason why the Earth is a sphere. As the philosopher, he wants to know why it's a sphere. Okay? And the proof is simple. The principles are right there. We've already enunciated them. We've agreed that all heavy matter seeks the center of the Earth, because the Earth is the center of the universe. All heavy matter seeks to be in the same place, the center of the universe. Therefore, what's the equilibrium? When everything wants to try to get to the same place at once, when all the Earth and all the heavy things, the earth and the water, everything wants to get to the same place, what's going to be your equilibrium thing? A sphere. Right? They're all going to try to glom on, and they're all going to be this symmetric object, all trying to get to the center. And that's exactly what gravity does. Okay? He has it's a very nice explanation of gravity, actually. Okay? And this is why the Earth is a sphere. You can see Aristotle's thinking here. This is a step beyond the speculative philosophers. No, this is progress being made. And this mental framework that Aristotle gives us is very comfortable in the Western mind, okay, and stays with us, like I say, for a long, long time. In some sense, it has stayed with us even today. All of his facts are wrong. All of his principles are wrong. But where he's trying to argue from is fundamentally sound. You have to give Aristotle credit for that. So one more look at the cosmos, and then I'll take some questions. So we have this simplified picture here of the Earth in the center. There's a ring of air around the Earth, and there's a ring of fire around that, because that's their natural place. Air will naturally want to go up, so there's a layer of air above the Earth, and then there's a layer of fire, which is lighter than air above that, and then you've got the moon. And once you've got the moon, you've got the ether. The moon is made out of ether, and all the planets above it are made out of ether. Remember, everyone knew that the moon is the closest thing to the Earth, right? Because the moon will occult anything in the sky. It'll block anything in the sky as it moves through the sky. And so therefore, clearly it is the closest thing to the Earth. No question about that. And once you get to the moon, you've got the ether, and you're finished with the earth, air, fire, and water. Notice that Aristotle's universe is a very interesting one. It's fundamentally a static universe. If everyone was left to their own devices and nobody disturbed anybody, then the planets, the 7 planets, would move around in their eternal cycles, and the earth and the water would be all in a sphere, not changing anymore. The air would be around it, and the fire would be around it, and the universe basically would be static. There would be fundamentally no change to the universe, certainly no change here on Earth. Okay, everything would be locked in because everybody would be in their natural place. Oh yes, the heavens would still be moving in their eternal cycles, because that's what they do. That's their natural motion. Okay? So Aristotle is looking for, like, when everything calms down and everybody is where they're supposed to be. And if it wasn't for outside forces, you would basically have no change at all, no fundamental change at all. Why do we have change? Clearly, our world is changing all the time. He has a reason. He's got to find one, right? There's got to be a reason for everything. It's the moon. As the sphere of the moon moves around, not the moon itself. Remember, the moon is attached to a sphere. Okay? He basically is on board with Eudoxus. He's going to modify Eudoxus's model and make it physically real. But the sphere of the moon is turning around, and it's stirring up the ring of fire. And the ring of fire is stirring up the ring of air. And that's where we get all the weather and the storms and this and that and all the craziness and the rain, and we have life as we know it. We have the world as we know it. We have the changing earth, air, fire, and water. So because of the old sphere of the moon is always stirring up the pot. There's got to be a reason, a fundamental principle for everything. And Aristotle is very good at finding them. Aristotle says that the universe is eternal. Okay, this basic cosmology has gone back to as far as, it has always been this way. And this is an important tenet of his. This will be an embarrassment to the church, the Catholic Church, when it adopts all of Aristotle's thinking as its fundamental cosmology. This was a sticking point because the earth is created in Genesis by God. So here's a problem where the philosopher, which is what he was called, is wrong. And the church didn't like a lot of wrong things. They weren't into wrong things. So they didn't like the fact that Aristotle had to be wrong on something, because then that would question whether he was right about other things. But this was a sticking point that Aristotle made very, very clear, that the universe is eternal and not created. And this is one of the conflicts that the church had to smooth over. No problem. Thomas Aquinas was very much up to the task of smoothing over anything that needed smoothing over. So let's just take a last look at Aristotle's cosmology. Here is Eudoxus's model in a nightmare. Okay? Eudoxus, Aristotle works with one of Eudoxus's pupils, another mathematician by the name of Calypsis, and they together decide that these spheres of Eudoxus have to be real. They can't just be mathematical objects, but they have to be real spheres which interlock, which have gears, which one sphere will be turning the other sphere, and they all have to work together. A real nightmare. They wound up deciding that they need 55 spheres, not 27 spheres, to make all this happen. And it's so impossible, so crazy, you don't even know. Aristotle clearly never understood the whole thing, but he did know that it had to be more complicated if he wanted to make these things real, and they had to be real. The ether was a real substance, as special as it was, and the substances had to somehow or other be touching each other so that the one turning could make the other guy turning, and the left, the elbow had to be connected to the, that kind of thing. And this idea is incredibly complicated, and it was soon abandoned by the mathematicians. Mathematicians will look, if you're going to go this way with Eudoxus's model, we really can't say. Besides, it didn't handle, the brightness problem. We really need to handle the brightness problem. So we're going to have to find something more powerful than Eudoxus's model. We're going to have to move away from just simple concentric spheres. But interestingly enough, the overall culture, the educated man of society, up until the time, and through Copernicus, up until the time of Galileo, when he has to be still fighting these ideas in 1632 with his great dialogue on the two universes, still fighting the ideas of Aristotle. This idea stays in the common wisdom, the common idea of these spheres made out of ether, these crystalline spheres which are weightless and invisible, and the planets are attached to them, and they're made of thicker versions of the ether, and that's why they shine with the light of the. And this fundamental idea stays for 2,000 years without the details. No one wants to try to understand the details of this. The mathematicians are working on another. We understand the mathematicians are working on another model which we can't possibly understand. And as a matter of fact, Europe went through hundreds and hundreds of years of no one being able to understand it in the Dark Ages. But this fundamental idea was simple enough to grasp, that somehow or other, the 7 planets were attached in some way to these beautiful crystalline spheres that we can't see, and they're all revolving around in some way. They're all being driven by the prime sphere outside, the primobium, the mover of all. And of course, it's very, very nice for the church to say, well, that's of course moved by God. Aristotle didn't need that, but he left very, very conveniently this outside sphere, which was the generator of all the other complex motions inside. And that clearly was the job of God to make that happen. So although this idea is hopelessly complicated and you couldn't even build it physically if you really wanted to, this stayed as the common conception of the this was taught in the universities, in the University of Paris in 1100, in 1200. This was taught. This was probably taught to Newton as a young undergraduate. Probably some old professor was still teaching this in his class. This conception of the universe. And, again, like I say, here we have Dante's universe. This is Aristotle's universe. Okay? Dante just simply called him the master. In general, in the High Middle Ages, he was just simply called the philosopher. Didn't even have to give him a name. Everyone knew who the philosopher was. That was Aristotle. Okay, so that we'll have more to say about Aristotle as we get further into his theory of motion, but we don't need to go through that right now. Any questions about this presentation before we move on? I would like to start the next presentation if we could. Any comments about the ideas of Eudoxus and Aristotle? Okay, then with that, let me see if I can find. We really now, oops, wrong one. Don't want the Word document. I want the PowerPoint. Here we go. Okay, we now really move into the world of mathematicians, and we will stay in this world now for the rest of our course. We will leave the philosophers behind, and we will take up the methods of Eudoxus, and we will follow them through by people who learn from Eudoxus, people who've learned from Euclid, and they now want to go ahead and build mathematical models, primarily geometric models of the heavens and their various aspects, and I will show you many, many wonders of what the ancient Greeks were able to do. The first one I have, I think we can, I don't know, we've got 6 minutes, see if we can do this. 2 wonderful videos I gave to you on Eratosthenes. Please go ahead and take the time to watch the Carl Sagan 6-minute video. It's a wonderful explanation of what I'm going to do now. He does it, better than I do. He's a wonderful, as you know, teacher, expository of science, and he did a beautiful job in that video. Please go ahead and watch the Carl Sagan demonstration of Eudoxus's model of measuring the size of the Earth. So here we have the library at Alexandria. Alexandria, of course, forms the empire, the joint empire, joining the Persian Empire with the Greek world, and we have this confluence of ideas, and this brings us into the Hellenistic world, where the Babylonian influence now becomes important along with the Greek geometry, and we have really a different kind of mindset. And we have people like Archimedes, for example, and Eratosthenes and Aristarchus, and ultimately Ptolemy. So this is this new world centered here in Alexandria and coming at the crossroads of the Greek world and the Babylonian world and the Egyptian world itself. So it's a tremendous place of intellectual ferment, and Alexandria does become the intellectual center of the world, throughout the Roman Empire, throughout the days of the Roman Empire until that was destroyed. Here we much mention Euclid. Euclid is the next great figure. Euclid comes right after Alexander, and this is a famous picture from the School of Athens by Raphael. And this is wonderful. This is Euclid here, and you can see he's surrounded by children, and he's got his slate teaching. And this is Raphael reminding us that yes, Euclid is the founder. He is one who writes the Elements. He's the one which you learn from. Everything begins. You begin your education with Euclid, and he has him surrounded by children here, learning the elements of geometry. A little geometry. I don't think we are going to be able to finish this. We'll finish, but let's go as far as we can. I know it's been a long time since most of you have looked at geometry, but The geometry that we need is not all that difficult and not all that advanced. And I think even for the old cobwebs of long, long ago, these things may resonate. Parallel lines. We have these two parallel lines here, and this line that cuts them is called the transversal. It sets up a number of angles. Angle A and B are called alternate interiors. It's either on either side and they're both inside. So they're alternate interior angles. Somewhere in the back of your mind, that's a phrase, that's two words that go together. I know they're there. Alternate interior angles are equal for parallel lines. Transversals create equal alternate interior lines. A and C are called corresponding angles. They are both on top of the parallel lines cut by the transversal. They kind of, the word is they correspond to each other. They're equal for parallel lines. And the last are vertical angles. They're just having nothing to do with parallels. When two lines cross, these two angles are equal, as well as these two angles here are also equal. So alternate interior angles and corresponding angles go with parallel lines, and vertical angles go with any two lines which cross. Right triangle. Okay, we have the Pythagorean theorem. We have our A, B, and C. The sides are called little a, little b, and little c across from those vertexes. The side opposite the right angle is called the hypotenuse, and we have the Pythagorean theorem. Okay? A squared plus b squared equals c squared. We have the definitions of the trig functions. We really only need cosine for today, well, for tomorrow, for next week, I mean. But the sine of this angle A is the opposite over the hypotenuse. So the sine is the opposite length over the hypotenuse length. It's a fraction. The cosine of A is the adjacent over the hypotenuse, and the tangent of A is the opposite over the adjacent. These are the definitions of the trig functions for a right triangle. And finally, we have three properties of a circle that we need. These are not bad. These, I think, seem reasonable. If you draw a tangent line to any point on the circle, that line is perpendicular to the radius line at that point. What's a tangent line? It's a line that just touches the circle at that one point. It just kisses the circle at that one place. That line, wherever that place is, where it just touches, is perpendicular to the radius line that you would draw up to that point. An important property that we'll need. We'll need the circumference formula. Circumference of a circle is 2 pi r. And we'll need the very important proportion for a central angle. An angle where it's coming from the center of the circle, theta. That angle is in a very nice proportion. It's kind of a sing-song. Theta is to 360 as the arc it makes is to the whole circumference. Very nice, very reasonable. Proved of course, in Euclid. So the angle is to the whole 360 as the arc it makes to the whole circumference. So theta is to 360 as S is to C. All right. Don't want to rush things. And this is a fun thing to show that the altitude of the North Star, here we are at 42 degrees, where our latitude is 42 degrees. Well, that's the altitude of the North Star. Okay? The North Star is actually your altitude when you stand on the Earth. And I'll show you why that is next time. We'll pick it up from here. Okay, so any questions on anything at all? Any questions on the geometry? Anything I went through too fast on those basic ideas from geometry? I gave you a lot: parallel lines, right angles, and circles. Any questions, any comments on that? Are you with me? Are we doing okay? All right, then I will take that as a as a tentative yes, and I'll stop our recording here.